Let us look at composition of functions. Let's say we are given sets A, B and C and none of them are empty sets. And then we have a function which maps A to B and another function G which maps B to C. Now, very clear, domain of G is B and domain of F is A. Now the idea is to go from A to C. So f of A is equal to B and G of B is equal to C, where A is in set A, B is in set B and C is in set C. Now we can also combine these two functions into a compact form. G of f of A is equal to C, which is also written as G of f of A. So G of f of A is composition of functions G and f. Now G of f of A is equal to G of f of A. In general, G of f is not equal to f of G. That means the sequence in which we carry out these operations is very important. Even if G of f is defined, f of G may not be defined because of inconsistent domains. Now G of f is defined only when the range of f is a subset of domain of G. So what does that mean? That means when we evaluate f of A, it should give us a result which is there in the domain of G, that is in B. Now, the composition of any function with the identity function is a function itself. Remember, identity function maps an element to itself in the same set. So, I sub A maps A to A and F composition I sub A is equal to F and I sub B composition F is equal to F. So there is no impact of taking a composition of a function with the identity function. Now if F maps A to B is a bijection, then for every A in A, f of A has a unique preimage. F of A is nothing but B. That is an element in B. So if A to B F is bijection, then remember it is 1 to 1 and on to. That means every element of B mapped by F has a unique preimage. And how do we understand this? F inverse of f of A. See, f of A gives us B. The inverse of B is A, which implies F composition F inverse is equal to I sub B. Now, composition of functions is associative. So let's say we have a function f which maps A to B, G maps B to C and H maps C to D. Then H of G of F is equal to H of G of F. Composition of bijective functions is bijective. So here if F maps A to B and G maps B to C and F and G are bijective functions, then G of F inverse is equal to F inverse composition G inverse. This is called reversal law. Remember, I mentioned that the order matters when we are composing functions. So the order is important in composition Let's say g of f of a is equal to c. Now look at this. What does G need? G's domain is the set B. That means it needs an element from the set B. So G needs B. But what do we have as of now? We only have A, which is the starting element from set A. So since G doesn't have B, G asks F to give B by giving it A. Now f of A evaluates to B, which goes as an input to G, and then G gives us C. And because of this, in general, G of f of A is not equal to f of G of A. Look at it like that here. A is mapped by F to B and G maps B to C. So the composition of functions is nothing but carrying out the functions in a linear fashion from inside out. So first we evaluate f of A and then we evaluate G. And remember, here we have only two functions. We could have multiple functions. Okay, now let's look at an example to understand it concretely. Let A be equal to the set 0, 1, 2. B be the set 0, 1, 4. C be 0, 1, 2. Now F maps A to B. And the rule is f of A is equal to A square. G maps set B to set C. And the rule is G of B is equal to square root of B. Then what would be the mapping? Since there are only three elements, we can actually do the mappings. 0 maps to 0 by the function f. 0 square is 0. And then square root of 0 is 0. Then we have f maps 1 to 1, g maps 1 to 1. Then f maps 2 to 4 and g maps 4 to 2. So g of f of A is equal to g of f of A, which is equal to g of, now f of A will give us what? A square. So g of A square. Now g will do what? It will take the square root of A square, which gives us A. So where A is in the set A square is in the set B, and square root of A square is in set C. Now in this particular case, f and g are inverses of each other. We know square and taking the square root are inverses of each other. So A is mapped to A square by f and g takes the square root of that square, which gives us A. Same is the case when we reverse the composition. So g maps B to square root of B and f maps square root of B to square root of B square, which is nothing but B. Now g of f is equal to I sub A, set A. That is the identity. Composition of this is identity in A. Similarly, f of g is equal to I sub B. Now, how does this work out? Okay, let's take it one by one. G of f of A from A, set A, is equal to G of f of A, which is G of f of A gives us A square. Then G of A square will take the square root of this A square, which will give us A. But remember, A is now in C. It is not actually moved from A to C, but the A that we have got from G is in the set C. Since C is equal to A, see C is 0, 1, 2, 0, 1. Since C is equal to A, the composition G of F gets us back to A. Because if the two sets are equal, then they are the same set. Since C is equal to A, the composition G of F gets us back to A. So G of F of A is equal to I sub A of A. And in the second case, F of G is equal to I sub B. We reverse the order of the function in the composition. F of G of B. Because now here what happens? G's domain is the set B. So we start with an element from the set B. So first G is evaluated and then F. So F of square root of B is equal to, now F will take the square of that. So square root of B square, which is equal to B, which is in the set B. So since we started with B and returned back to B, F of G of B is equal to I sub B of B. A little bit tricky, but make sure that you understand this. Notice that F and G are bijective. That is 1 to 1 and on to. 0 maps to 0, 1 maps to 1, 2 maps to 4. And G is also bijective. Why? Because G maps 0 to 0, 1 to 1 and 4 to 2. And in both cases, that is in case of F and in case of G, there are no leftovers in the codomain. Hence, a reversal law does apply here. So G of F inverse, or we can say inverse of G of F is equal to F inverse composition G inverse. But F inverse is what? F and G are inverses of each other. So F inverse is equal to G and G inverse is equal to F. So we substitute this in the above. We get G of F inverse is equal to G composition F. Now, this is not in all cases. This is the case only when the two functions are inverses of each other. So the inverse of the composition is equal to the composition of the functions. That would be only when they are inverses of each other. Now, in the previous session, we had seen some examples for inverses of functions. Now that we have learned composition of functions, let us verify them by composing the function and its inverse. So we have f of x equal to x cube and f inverse of x equal to cube root of x. So f of f inverse of x is equal to the f inverse of x gives us cube root of x. F takes cube root of x and cubes it, giving us back x. Similarly, f inverse of f of x is equal to f of x gives us x cube. F inverse of x cube gives us cube root of x cube, which is again x. So whichever function we start with, applying the other function brings us back to where we started. So that means they are truly inverses of each other. Let's look at the second example. F of x was 2x plus 1 and we derived f inverse of x equal to x minus 1 by 2. Now, f composition f inverse of x is equal to f of x minus 1 by 2 because f inverse of x gives us x minus 1 by 2, which is equal to, now we substitute x minus 1 by 2 into 2x plus 1. So we get 2 times x minus 1 by 2 plus 1, which is x minus 1 plus 1, which is equal to x. Now reversing the order, f inverse of f of x equal to f inverse of 2x plus 1, which is equal to 2x plus 1 minus 1 by 2. So here in the inverse part of it, x is replaced with 2x plus 1. So that is why we have 2x plus 1 minus 1 divided by 2. Again, which gives us x. Therefore, F composition in F inverse is equal to the identity in range of F. And F inverse composition F is equal to the identity of domain of F. So that was composition of functions. That's it for now. Bye.